Hello, in this video we are going to talk about matrix multiplication. And I've put up here 5 different matrices of different sizes, and then there's 6 problems that I want to talk about. So we'll try and get through these, and each one will show a little bit different scenario with matrix multiplication. Now matrix multiplication is different from scalar multiplication with matrices. For that it would be like taking 5 times A, so you just multiply every entry by 5. Pretty easy. Matrix multiplication is a little bit more involved. So for number 1, I'm going to go A times B. So I'm going to rewrite each matrix here. And remember how matrices, we mentioned a little bit about how they can be thought of as a collection of vectors. You can think of them as each row being a vector, each column being a vector there, or each row being a vector. And a lot of times that's how matrices are used, to store vectors, to store the information of vectors. I bring that up because when we talk about matrix multiplication now, you're going to notice something very similar to how you multiply vectors with the dot product. Okay, so let's go through this. It's very important that you know the dimensions of your matrices when you do this, because you cannot multiply every matrix together. Or I should say, if you take 2 matrices, it's not guaranteed that you can multiply them. The dimensions have to match up. They don't have to be the same dimensions, but there is something that has to match up. Specifically, the column of the first matrix has to be the same as the row of the second one. So since there are 2 columns in my first matrix, there must be 2 rows in the inner matrix. That is because when I do matrix multiplication, I'm going to be taking the first row and multiplying it with the first column. And so the number of terms in the first row has to be the same as the number of terms in the first column. Once you check that that's the case, the resulting matrix, after you multiply them, is going to be of the size of these outer terms. It's going to have as many rows as the first matrix and as many columns as the second one. So a lot of times I draw my matrix already with the blanks. I know this is going to be a 2 by 2. Then how do I fill it in? So now going through what I mentioned before. For my first term right here, I'm going to take the first row times the first column and do a dot product. What that means is I'm going to take 2 times 3 plus 3 times 1. Okay, so I took this 2 times this 3 plus this 3 times this 1. It's a vector dot product is what we're doing. Okay, what about our second entry? So we can move down to this one right here. What is the entry of that if we're doing notation? It's the entry A, second row, first column, A sub 2, 1. So what do? I take the second row, multiply it with the first column. So I go -1 times 3 plus 4 times 1. I'm going to go over here. What is this entry? This is first row, second column. So how do I do this entry? I take the first row, multiply it with the second column. Or more specifically, I take the first row and dot product it with the second column. So we go 2 times 7 plus 3 times -5. Okay, and the last one. This is entry second row, second column. So I'm going to take the second row and second column, multiply them together. So I get -1 times 7 plus 1 times -5. Okay, and then we go through and we just simplify each of these. So I get 6 plus 3, so I get 9. I get -3 plus 4, giving me 1. 14 minus 15 is -1. And -7 minus 5 is -12, and that's my resulting matrix. Notice how it is a 2 by 2, matching up with the rows of the first matrix and the columns of the second. Let's try number 2. Here I'm going to illustrate something because now we're finding B times A. So the same thing, it's just I'm changing the order of my 2 matrices. So it's this times 2, 3, negative 1, 1. And I'm sorry, I realized I copied this matrix incorrectly with a 1, so I'll keep with that idea for this one. Okay, so it's still 2 by 2 and 2 by 2. Get in the habit of labeling your dimensions first. Because those match up, it's okay to do matrix multiplication. And what is the new matrix? It's going to be a 2 by 2 because of those outside terms in your dimensions. So for the first slot, we take the first row times the first column. So 3 times 2 is 6. 7 times negative 1 is negative 7. And then I'm going to go second row times first column. 2 times 1 is 2. And negative 1 times negative 5 is positive 5. All right, let's go first row, second column. 3 times 3 is 9. And 7 times 1 is 7. And finally, we go second row times second column, and we get 3 minus 5. Okay, 6 minus 7 is negative 1. 2 plus 5 is 7. 9 plus 7 is 16. And 3 minus 5 is negative 2. What do you notice about these two? Well, you should notice they're different. They do not equal each other. Is that a little bit surprising? Because we did a times b and b times a. And typically, with multiplication, you're comfortable with the idea that it's commutative. It doesn't matter if I go a times b or b times a, the result is the same. Well, not the case with matrix multiplication. It is not commutative. The order in which you multiply matters. If you multiply in different order, it's going to give you a different answer. All right, let's try number 3 now. I'll clear the slate. All right, we're going to try number 3. So the dimensions of B is 2 by 2, and the dimensions of C is 2 by 3. 2 rows, 3 columns. So I can write those down, 3, 7, 1, negative 5. So first we need to think, can I even multiply these together? Well, because the column of the first one matches up with the rows of the second one, yeah, we can. But what is the resulting matrix this time? 2 by 2, 3, 2 by 3. We look at the outside terms, it's going to be a 2 by 3 matrix as a resulting one. So we're going to get 2 rows, but 3 columns as the result. Okay, so we can run through this. For this first slot, it's first row, first column, and you see how those terms match up. So we have 6 plus 7. Then we're going to go second row times first column, giving me 2 minus 5. We'll go back to first row, second column, negative 12 plus 21. And then we go second row, second column, negative 4 minus 15. And let's move on to first row, third column, so that's 33 minus 0. And second row, that's 11 minus 0. Giving me the matrix 13, negative 3. So just going through our arithmetic here. Lots of room for small errors again here, so be careful. 33, 11. Okay, that's the resulting matrix. Notice how it is a 2 by 3 as we wanted. Number 4, B times D. So I get 3, 7, 1, negative 5, and D, the dimensions of D are a 3 by 2, so we go 4, 2, 10, negative 2, 7, 1. Okay, can I multiply these? 2 by 2 and a 3 by 2. You should recognize, cannot. Those inside dimensions, or the columns of the first one, does not match the rows of the second one. So I cannot create that matrix. And think about it, because the process of matrix multiplication is to take the first row times the column. Well, that doesn't match up. I'm going to have a 3 times 4, a 7 times 10, but what times this term down here? I don't have a term from my first matrix to multiply with it. It creates an issue. So for number 4, we're just going to say not possible. Can't do that. Okay, I'll clear this slate and we'll try a couple more. All right, we're going to try number 5, which is DE. So I'll write them down here, and you can start thinking about, can I even multiply these? Or am I wasting my time by writing these out? Hope not, because it's a lot of terms. So the dimensions of the first one are, well, we already established it, 3 times 2. And the dimensions of the second one are 3 by 3. So can I multiply? Oh, no. Wasted my time. I can't. The columns of the first one does not match up with the rows of the next. I cannot multiply these. All right, so number 5, not possible. Not possible. Okay, so we can move right on to 6. C times E. Well, is this one going to work? It is, and I can look up here. So that inside terms match, it's going to result in a 2 by 3 matrix. So I'm just going to rewrite that first matrix. I'll save a little bit of my work from the previous one. And I will write the C matrix 2, -4, 11, 1, 3, 0. Okay, what is this going to result in? We said it would result in a 2 by 3 matrix. So 2 rows and 3 columns. Something like that. So we're going to take a first row times the first column. Now I have 3 terms to all add together. So I go 2 times 4 is 8, plus 4 times -1, which is 4, plus 11 times 3, which is 33. Now we'll move on to second row times first column. So I go 1 times 4, 3 times -1, and 0 times 3. Now I want to remind you how I'm figuring out what columns to multiply together. Because remember, I think about, if I'm trying to fill this in, this is the term first row, second column. So I'm taking my first row, multiplying it with the second column. So I think about what entry I'm on, and those are the rows and columns I multiply together. 2 times -2 is -4. -4 times 0 is 0. And 11 times 6 is a whopping 66. Let me stretch out this matrix a little bit. Give me some more room. For the next one, I'm going second row times second column. So I get -2. 3 times 0 is 0. And 0 times 6 is 0. All right, I like that one. And for this last one, the exciting last one, we'll get an exciting color. We'll go first row, third column. So we get 2 minus 8 and minus 22, which is 11 times -2. And now second row, third column for that last slot. Second row, third column. 1 plus 6 plus 0. Okay, and now we just go through and let's simplify each of these. 8 plus 4 is 12, plus 33, 45. 4 minus 3 is 1. -4 plus 66 is 62. And then -2. 2 minus 8 is -6. Minus 22, -28. And lastly, 1 plus 6 is 7. And there you go, our resulting matrix. It is a 2 by 3 matrix, as expected when we looked at the dimensions at the start, because those outside dimensions provide the dimensions of the resultant matrix. So there you have the basics of matrix multiplication. Couple things to keep in mind. It is not commutative. It matters the order which you multiply. You cannot multiply all matrices together. The dimensions have to match up like we talked about. The columns have to match up with the rows of the second matrix. And then it results in a matrix of the size where you take the rows of the first with the columns of the second matrix, and that's the size of your new one.